Okay, great. So hopefully everything is working properly then. Okay, so welcome everybody to the second seminar of the in our N3AS Seminar series of the semester. We are very happy to have Wynn joining us from Haverford College, and he's going to be talking to us about the cooling of Cassiopeia A. So please, whenever you're ready, we're happy to hear.
Okay, thank you. Thanks to the organizers and also to Sophia for inviting me to give this talk. So I'm giving it on behalf of the my collaborators here, shown here, and the results, the updated results that we'll be talking about are in these two papers shown here. So moving on to the. I should also let me also say that feel free to interrupt, although I can't see any hands raised. I'm sure the organizers can flag me if they need to interrupt me if you have any questions. So I'm happy to do that. So for this relatively short talk, my outline is pretty simple. The first half of the talk, I will talk about the observations of the cooling of the neutron star in Cassiopeia A, which I'll just call Cass A for short. I'll just talk about the observations themselves. And then in the second half of the talk, I'll give a brief introduction to neutron star cooling theory, and then concentrate on the effects on cooling of superfluidity and superconductivity, and how, and then apply this neutron star cooling theory to Cass A to learn about superfluidity and superconductivity, and then I'll summarize. Okay, so this start off with a pretty picture. So this is a multi-wavelength image of the Cassiopeia A supernova remnant. For those of you who are sky watchers, I have a finder chart up in the upper right here that shows where Cass A is relative to the constellations Cassiopeia and Cepheus. So it's located here. However, it is pretty faint and diffuse in optical, and so you wouldn't be able to see it with your eye. Going back to this image, this is, like I said, it's a multi-wavelength image of the supernova remnant, so the remains of the supernova that went off. And the red is infrared from the Spitzer Space Telescope. Yellow is optical from the Hubble. And the green and blue is X-rays from the Chandra Space Telescope, which is shown here. And so we know the age of the supernova by measurements of basically the expansion of the remnant, basically tracking the knots and filaments that you can see over time. We can back extrapolate to get when the supernova went off, and that is estimated to be in the year 1681, plus or minus about 20 years. So that gives us the age of the supernova remnant and the neutron star to be about 340 years old. If you look carefully at the remnant, what you'll see is a bright blue point source at the center of this remnant, and this is the neutron star. It wasn't as it's blue, so it's only observable in X-rays, detectable in X-rays, and it was only when the Chandra X-ray telescope was first launched in its first light image that this point source was detected. And after about 10 years, about 10 years after its discovery, we identified it as the neutron star, and being with an age of 340 years, that makes it the youngest neutron star that we know of. And through a series of observations, and so the next following few years, we measured the temperature of this neutron star and showed that it was rapidly cooling, and that's can be attributed to superfluidity and superconductivity in the neutron star, which I'll talk about. So that was using these initial 5 to 6 observations by Chandra. But so now I'll talk about an update. Basically, we now have 14 sets of observations over 19 years given here. And basically, what we have are the spectra, the X-ray spectra of this point source. And that's what's shown here in the bottom left here, the flux spectrums of counts per, as a function of energy. And so all 14 observations here are stacked. Okay, and so what we do to measure the temperature is that, well, to measure parameters from this spectrum is to fit it with a model. And there are a couple components to the model. The first is a component that's due to interstellar absorption that's parameterized by this value of this parameter NH. Okay, so this is to account for gas and dust between us and the neutron star. So from the Earth to the neutron star that absorbs X-rays. And so this NH parameter parameterizes how much material is between us and the neutron star. And so the higher the value, the more absorption that there is. The second component to the model is neutron star atmosphere. And so just like the if we were to when we look at the sun or if we look at another planet, what we're seeing is the atmosphere of that object, and it's the main things that determines its spectrum is its temperature, and also obviously its distance. For neutron stars, there's a dependence on its mass and radius as well. And so when we fit these 14 observations of spectra with this model, we can extract parameters like the mass and radius, the temperature, and so forth. Okay, and what is shown in the top right panel here is constraint our measurement of the mass and radius using these 14 observations, and you can see that it's not that constraining. Okay, so there's not a strong dependence on mass and radius for the Cassiopeia A spectra. Okay, what we're interested most primarily is in the temperature. Okay, so what temperatures do we measure from these 14 observations? Okay, and that's shown here. This plot is showing the temperature as a function of time, so year up here and Julian date down here. I'm going to show two sets of numbers for most of the things, for most of the cooling rates I'm showing for Cassiopeia. I will show two numbers. Okay, and those two numbers are because is based on a kind of a model assumption. Is one is the first number is whether this NH parameter that we we fit them as a model. I mean, that's a model parameter that we fit to the observations, is whether it's constant over all 14 observations. And so if we assume that, and that's plotted here, so this line is that assumed constant value. Well, it's a fitted value, but we're going to assume that's the same value for all 14 observations. You get this, and then you measure the temperature and you measure the cooling rate, and this is the number you get. Now, if you assume that that this NH, or you allow this NH value to vary between each observation, okay, and that's the values are plotted here. You can see that they're scattered around the constant value. Then you get a slightly higher cooling rate. Okay, I'll just note that from the fit statistics of the fits, the variable NH is more preferred. Okay, so I'll concentrate on this, but I'm happy to discuss this more if people have questions in the discussion. I see that, is there, let's see, somebody?
Yeah.
Okay, yeah, so I see your question, but if you want to ask it, go ahead.
George used to doubt the cooling observations. Has he changed his mind?
So I'll get to that in the next slide. From speaking to him, I can't say for the most recent. Well, I'll get to that in the next slide. And you can ask again if I don't answer your question. Going back to the slide, the basic end result is that from these 14 observations over 19 years, we measured that the neutron star temperature is cooling at a rate of about 2 to 3% per decade. Now, advancing. Oh, there we go. Oops. Okay. Prakash has mentioned something which this slide illustrates. So there is a I would say debate or controversy over this cooling rate, and that's shown here. So there's another set of data taken by Chandra. That's 4 sets. So this set of data is better suited for measuring the spectrum of the neutron star. Okay, whereas these the 14 set of 14 that I'm showing here is better suited for studying the supernova remnant, the big remnant, whereas the 4 are better suited for the neutron star. However, you can see that there's only 4 observations, and they span a much shorter period of time. So what Prakash mentioned is George Pavlov's work with Bettina Basselt. They published work in 2018, which of course they only had these 3 observations: 2006, 2012, and 2015. There has since been a 4th observation. And so the end result is I analyzed and put through the same fit procedure and so forth. And what I get is shown by the red points here, the 4 red points. And if I measure the cooling rate, both if I assume a constant NH or a varying NH, the cooling rates are somewhat lower. Okay. But again, I'll point out that the data actually, the fits actually prefer this varying NH. And so what you can see is that taking this varying NH value, cooling rate, that we're actually consistent within 1 sigma here. Okay. So the temperature is cooling at a rate of between 2 to 3%, okay, within the uncertain. So in terms of direct answer to Prakash's question, I would say that based on his on the 3 measurements that he had in the paper that he published in 2018, he would still dispute our cooling rate. I haven't spoken to him since the 4th observation came out, so I can't speak whether he believes it more or still is opposed to it as much. So yeah, so and I can talk more about this after the talk in the discussions if people are more interested in this issue and why there might be some that's some of the technical details of this. Are there any other questions at this point? So this is the first half of my talk on just the observations. So I'm going to move on to the cooling theory, and so what do these observations imply about cooling theory, and what can we learn about neutron stars and basically superfluidity and superconductivity from this measured cooling rate? Okay. No questions? Okay. So this is going to be a very brief introduction into neutron star cooling theory. And the idea is the following, that if a neutron star is born hot, and with any object that's hot, it's going to cool over time. And how it cools over time and can be determined mathematically, physically can be determined very easily, and it only depends on 3 parameters. Okay, in the case of the neutron star, it depends on the heat capacity, basically how much heat, how much energy is stored in the neutron star. The thermal conductivity, so the thermal conductivity determines whether this object has a temperature gradient within it, or whether it's isothermal, because the conductivity determines how the heat is transported within the object. And then finally, the emissivity, or how rapidly does it emit or lose its heat. Okay. So determining the neutron star cooling is calculating that is relatively easy if you have these 3 ingredients: the heat capacity, thermal conductivity, and the emissivity. Okay. The complication, of course, is that these 3 parameters depends on lots of unknowns or uncertain physics. And those things are, for example, the proton fraction. What type of particles? Is it just neutrons, protons, electrons, and a smattering of muons, or are there other particles present, condensates, hyperons, free quarks, and so forth? And also, what I'll be concentrating on is superfluidity and superconductivity. Okay, so these parameter things like these feed into what is the heat capacity of the neutron star, what's the thermal conductivity, and what is the emissivity. Okay. Now, but once you have these, you can feed it into calculate how does a neutron star cool with time. And that's what's shown by this plot on the right here. This is plotting surface temperature as a function of time. And these different curves are different theoretical cooling curves, or models for how a neutron star cools over time, depending on whether I have a high proton fraction in the core, so that I cool by what's called a direct Erka process, fast neutrino cooling process. And so it causes the neutron star temperature to drop very rapidly to low temperatures. Or there are different particle species like pion or kaon condensates. Or you can get curves, anything in this shaded region you can get by changing things like the superfluid and superconducting properties of the matter in the neutron star. And then these points are just various measurements of real neutron stars and their temperatures. Okay, so what you can, some generic properties you can see from these cooling curves is that there are basically 3 stages. This early stage where you see the temperature starting from high temperatures, it drops very rapidly here, 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 here. This is the stage in which the neutron star there's a strong temperature gradient within the neutron star, and so it's cooling and it's relaxing to a more isothermal state. Okay. And this state, how long this takes depends on the heat capacity and the thermal conductivity, and it can take between roughly 10 to 100 years. Okay. Let's see, 10 to 100 years roughly. Okay. And then in the first roughly a million years, the neutron star is cooling by neutrino emission. And that's because temperature is high, so that neutrino emission is the dominant cooling process or heat loss process. And then after a million years, the temperature drops low enough that the neutron star now cools, basically by emitting photons, okay, from the surface. Okay, that's at very late times. Okay, so that's a very quick, brief introduction into neutron star cooling theory. So let me talk about concentrate and talk about the effects of superfluidity and superconductivity on neutron star cooling. So you all know that electrons become superconducting when their temperature drops below a critical temperature. Right? When in fact then they become the electrons become Cooper paired, they become paired and become superconducting. In neutron stars, it's instead of electrons, it's the nucleons that become superconducting and superfluid that become paired, and the protons become paired and they become a superconductor. The neutrons can also become paired, but since they don't carry electrical charge, they're not conducting, they're what's called the superfluid. Okay, so you can just think of a superfluid as the neutron analog of a proton superconductor. Okay. Now, matter becomes superfluid and superconducting when its temperature drops below a critical temperature, which depends on the pairing energy, which is in turn depends on the Fermi momentum, which in turn depends on the density. So what I'm plotting here in this top plot is the pairing energy as a function of Fermi momentum, or there's a correspondence to the critical temperature as a function of mass density. That's what's plotted in the bottom right for different nuclear theories for what this pairing energy is. Okay. Now we don't know which one of these, if any, is the correct one, and the idea behind neutron star cooling theory is to try to use the observations of neutron stars at their temperatures to determine which of these, if any of them, is the correct one. So we're trying to determine which of these various curves is closer to the one in reality. Like I said, in neutron stars, there are 3 pairing types. In the core, the protons pair in what's called the singlet or S-wave state. And in the core, the neutrons pair in this what's called the triplet state. And while in the crust, the neutrons can pair in what's called the singlet state. Okay, so, and they each have a corresponding pairing gap, pairing energy plot similar to this. Okay. So the effect of superfluid, the matter, either the neutrons or the protons being superfluid or superconducting on the cooling there's 2 main effects. The first one is that when the matter becomes superfluid or superconducting, that suppresses particular neutrino emission processes. Okay, because that's basically, if you have a process that depends on protons and the temperature is such that it becomes superconducting, then basically those protons no longer participate in that process. So that process, its efficiency becomes lower. Okay, and so you can imagine that tells you that that should make the cooling slower, because you've basically suppressed heat loss mechanism. The second effect, though, is that becomes an extra neutrino emission process called the Cooper pair formation and breaking process, which is when you have pairs of neutrons or protons pairing, and they emit neutrinos which carry away energy. So this extra process is an extra neutrino loss mechanism, and so that can give you faster cooling. Okay, and so this just summarizes that the protons in the core, the dominant effect that it has is that it slows down the cooling due to the suppression of nucleon processes, whereas the neutrons in the core and the crust, their dominant effect is when they become superfluid is that they lead to faster cooling because of this extra cooling channel. Okay, so let me summarize this all in kind of an animation, which is shown here. Okay, I hope you can all see this animation as it's progressing. Okay, what's shown on the right panel here is this plotting temperature, surface temperature as a function of time. And so the 3 curves are this dashed curve that I've labeled N is if I assume that all the neutrons and protons in the neutron star are normal, and there's no they never become superfluid or superconducting. Okay, so this is how this curve, this dashed curve is how the neutron star cools over time. The PSF is if I allow the protons to become superconducting if the temperature drops below a critical temperature for proton superconductivity. Okay, and you can see that, as I said before, that the cooling is now much slower. Okay, so at a particular age, it's can't see my cursor. At a particular age, the temperature is higher because it's cooling slower. Now, if the NPSF is if I allow both the neutrons and protons to become superfluid and superconducting. Okay, and in which case, at early times, the protons become superconducting, and so I cool slower, but then the neutrons become superconducting, and suddenly I can get this rapid cooling rate. Okay. I'll note that I made this animation about 10 years ago, and when we first had our results and stuff. So I only showed the first 6 observations, Cassiopeia observations here. But like I said, we now have 14 that span from 2000 to 2019. Okay, on the left panel, what I'm showing is the interior of the neutron star. Okay, so going from low density to high density. Okay, so this is the outer crust of the neutron star, the inner crust, the core. And down here, this is just the blow up of the core region. And what these 2 sets of curves, okay, so this line, this dashed line is temperature. And this is the temperature of the and what I'm showing is the critical temperature here for superfluidity of the neutrons in the core. Okay, so when this temperature drops below this line, then the neutrons in that region, this region here, becomes superfluid. The neutrons out here are still normal. And this solid line is the neutrino brightness, or the emissivity of the matter. Okay. And so what you can see is some interesting effects. The first is that at early times, you can see that there's a temperature gradient in the neutron star. But at late, let's see, once it restarts. So at late times, basically, this is the temperature profile. It becomes isothermal. Okay, so it's the same temperature throughout. But once it resets, you'll see that there's a temperature gradient. There's a strong temperature gradient. Okay, and you'll notice that it's actually initially it's lower temperature in the core than in the crust, because the neutrino emission is more efficient in the core. So at early times, very quickly, it cools down the core, but that hasn't caught up. So there's a cooling wave that propagates out in the first 10 to 100 years through the crust of the star. Okay, so you can see here that it gradually becomes isothermal. The other thing you'll notice is that if you look at the neutrino emissivity, is that see, once it resets, you'll see that when the temperature drops below the critical temperature, you'll see a little bump start appearing in the neutrino brightness. So if you look carefully here, you'll see once the temperature drops below, you'll see this little bump start to occur. Okay, so that's the extra neutrino emission channel, the Cooper pairing formation that's giving you this extra rapid cooling. Okay, so the end result is that in order to fit the Cassiopeia observations, okay, the rapid cooling, we need both that the protons become superconducting at early times, so that the temperature is high at early times, but then by about the 1900, when the temperature drops below the critical temperature superfluidity, this extra neutrino emission channel turns on and it cools it very rapidly. And so that's what we're going through at our current time. Okay. And so actually, I think That's it. So let me summarize. So by main points is that by comparing cooling theory with observations, we can learn new things about nuclear and particle physics. And in particular for Cas A, we measured that it's cooling at a rate of about 2 to 3% per decade. And this allows us to constrain, basically determine what is the critical temperature for superfluidity, neutron superfluidity and proton superconductivity in the core of the neutron star. I'll also point out that there are, for those interested in multi-messenger, there are gravitational wave searches for Cas A. None has been detected yet, but they are being performed. And the final point that I want to make is there's a lot of excitement, and I'm involved in things like NICER, which is measuring neutron star mass and radius, because that has important implications for the nuclear equation of state, and it's an important parameters to measure. But I want to kind of highlight and make the point that we should be going beyond just measuring mass and radius, and comparing using neutron star cooling observations allows us to do that, because so we can measure things like superfluidity, superconductivity. There's many other observations and of neutron stars that can tell us other things, like transport properties, things like neutrino viscosities, whether there are hyperons and quarks and stuff. All of that is we can probe now with neutron star observations that go beyond just the bulk mass and radius. And let me stop there, and I'm happy to answer any questions. Thank you.
Okay, fantastic. Yeah, thank you for that really lovely talk, Wynn. I hope you'll all join me in a virtual round of applause here. Of course, let's open up the floor to any questions. And I see that Jim Latimer, you have a question. Please go ahead.
Yeah. Hi, Wynn. I noticed with some disappointment, according to your simulation, we have to wait about 100 years before we see any indication of a slope change. Or have you estimated how long it will be before the observations are good enough to see if that curve is actually correct?
Yeah, so I think you're right that it will be a while, and we need something like Chandra at that time. I wouldn't put too much into like the 100 years or so, because like I said, the simulation that I'm showing here was matching these initial 10 years of data, whereas we now have 20. So I think I can revisit these simulations to get a more updated estimate of when that would occur. But yes, it would still be 100 years or more from now.
All right, thank you.
Okay, I see Sanjay has his hand raised.
Wynn, thanks for that very nice summary of what's been going on with Cas A. It's exciting that the data seems to want some kind of cooling. So this is nice. And as Prakash said, maybe there are still some doubts out there about systematics. I'd love to hear about that later. But my question is, assume that this is in fact what we're seeing, that it is the cooling of the neutron star surface. And what this is offering, you're offering an explanation based on the pairing gap of neutrons in the 3p2 channel, right? That is the crucial ingredient.
Yes.
So you have to fit the data. What are the typical critical temperature profiles? Is it giving us some indication of some models of 3p2 pairing gaps that are working well and some that are not?
Yeah. So in terms of the the maximum, okay, so the critical temperature is density dependent. So it's the maximum value is roughly, when you take into redshift, is roughly between 5 and 10 times 10 to the 9 Kelvin. So between 5 and 5 and 10, 10 to the 8 Kelvin, sorry, which you can see here. And so that's, I think, pretty, again, within the standard picture of superfluidity and superconductivity, that's pretty robust. And the Peters, Shaturnen's work, our recent work, kind of shows that this is basically model kind of independent. In that work, we also it's kind of model this Cooper pairing formation energy gap, and you can actually split it into two pieces, one of which is model independent and one which is model dependent. And so in that paper, we put in different, we look at different models and stuff. And so yes, the bottom line is we are able to say which ones does Cassiopeia favor, which temperatures and density ranges would support the Cassiopeia interpretation of rapid cooling, and which do not.
Okay, and what is the typical density range? In this figure, I see that the neutron superfluidity requires to be present between, what is it, 6, so that's about 3 times nuclear density to 4 times nuclear density.
So maybe you're probably more familiar with something like this, where I'm showing the pairing energy as function of Fermi momentum.
Yeah.
You know, if I can translate that into here, if I just use the APR equation of state, I can translate that into temperature and density. But so I would say the ones that seem to fit the Cassiopeia data are things like in this mid-range here. Okay. So kind of, you know, you can kind of take it as a bias. It's the kind of the middle middle range of values and stuff.
I see. So you would require 3p2 pairing to be present up to 2.5, 3 times nuclear density.
Yeah. Yeah, that sounds about right.
Okay. Okay. I don't know if there are other questions. I don't see any other questions, so I may go ahead and ask you one more. We have no idea what are the processes, if there's any magnetic field decay in the crust, deep inside the crust. Can you hide a complicated magnetic field in the crust? And its evolution somehow affects the thermal evolution. Is that a plausible scenario?
Okay, if the magnetic field is not too high, so what I mean by too high is, you know, 10 to the 14, 10 to 15, and if it's below that, so it's kind of standard radial pulsar 10 to the 12, 10 to 13 or lower, then there, the heat that's generated from, you know, magnetic field decay and stuff doesn't have a strong effect. So something like that you can hide in the crust, and it wouldn't affect the cooling. It wouldn't strongly affect the observations of Cassiopeia if we kind of use Cassiopeia as a constraint. Now, if the magnetic field was much higher, something like 10 to 14, 10 to 15 Gauss, then you can have the magnetic field decay will heat the crust, and so kind of mask some of the effects that we see. And so there are papers that have kind of tried to explain the rapid cooling instead of invoking superfluidity and superconductivity. They invoke this magnetic field effects, much stronger magnetic fields to get you the same rapid cooling.
And in your opinion, are they plausible or are they, finely tuned?
Well, I mean, I guess I'll argue kind of from their point of view. Well, we're finely tuning our critical temperatures, but my counter is that, but that's what we're trying to measure. So, but you can say that it's kind of finely tuned because you tweak, you get the magnetic field just right, so you can get the rapid cooling. I mean, I think for CAS A, that's a little harder because there are other observations that kind of seem to argue against that. So I wouldn't say that there's zero chance that that's the case, but I wouldn't I wouldn't say that it's also strongly favored either.
I'm surprised you say that the scenario you're presenting is finely tuned, because you just made the claim that the gaps that the observations need are actually the gaps that nuclear calculations are providing. So in that sense, it's not, I would argue it's not finely tuned.
I mean, I fully agree with you, but again, I'm just arguing from the other side's point of view that they say we're tweaking the knobs just so that we get the value what we want. So it's a point of view type of thing, I guess.
Okay, thank you.
Just a short question. Can you hear me?
Yes.
So, is there any great modification needed from the initial papers that Sternin et al. And Danny Page et al. Wrote early when the cooling was reported?
Is there any large revision? No. I mean, on the qualitative levels, on the quantitative level, I would say yes. So we initially got a cooling rate based on basically these 6 observations, that the cooling rate was more closer to 3 to 4%. But it's actually now with more data with twice the baseline, we're getting about 2 to 3%. So but in terms of the overall qualitative picture, no.
Okay, thank you.
All right, it looks like Mia has a question.
Right, so this is dramatically simpler than these other questions. In this animation you have here, what's the model you're using for your normal matter cooling? I guess because if there was direct ERCA in the normal matter, I was surprised that the pairing would completely overtake it like that.
Yeah. So this is the dominant process in the normal matter is modified ERCA.
Okay.
Okay. So and I think the animation I'm showing here, I think I'm using APR, and the mass I'm using is like 1.6 or something. So it's below the direct ERCA threshold.
Okay, thank you.
Okay, it looks like.
Oh yeah, I should also note, since you pointed this out, there again, as with the magnetic fields, there are other papers who've argued that actually the mass of the neutron star is high and it's above the direct ERCA threshold, and so rather than this superfluidity argument for why it's rapidly cooling, it's because it's just transitioning into direct ERCA, so you're seeing this relaxation period. So there are works that make that argument too.
Okay, we have a question from Jiangqi.
Yeah, it's a nice talk. I have a quick question about the neutrino brightness after you hit the superfluidity.
Yes.
Deep inside the core, the pair breaking formation should be weaker, right? So you would expect the neutrino luminosity to decrease, but it seems high still in the deep core.
So I mean, you can see at So the extra neutrino emission is dominant at the transition. Okay,
But
so you can see here, right? Oops, I'll let it run. So what you'll see is that at late times, when deep in the core, you'll see that actually the neutrino brightness is actually lower than out in the
Yeah, but at this time, it still have very high luminosity at the core. Do you
yes,
see that?
yes,
But that's, I do not understand that part.
The core
Oh.
is to the right of the plot.
yes.
It's not shown here.
Oh, okay.
So
Okay.
you can see here, right?
Oh,
So the neutrino brightness is brightest at the transition. So
yeah.
right where the matter is just becoming superfluid. Okay, and so you can see deep in the core where the matter has been superfluid for a long time.
Okay.
The brightness decreases.
Okay.
It's lower.
But the later, but even in the center, it has a small increase. Is it because of the density?
So you can see that actually this profile, this critical temperature profile drops.
Oh, okay, okay.
Drops so this is just again the transition.
Oh, okay,
region.
okay. Yeah, thank you for the
That's where it's
explanation.
brightest.
Yeah, that explains a lot. Thank you.
It looks like Prakash has another question.
No, it's a legacy hand.
Okay, very good. All right, any further questions then? Sophia, go ahead.
Thank you, Wynn, for this really nice talk. I have a follow-up question, basically what Mia just asked you. There is this alternative explanation with the direct Erka and additional suppressing of that direct Erka to also consistently explain Cassiopeia. I vaguely remember it requires a much higher superconducting gap temperature for protons.
Yes.
Maybe it's in addition to what you presented today. Do you know any like updates? If we want to explain Cassiopeia using that combination of superfluid gaps?
I should say, so this is the critical temperature for superfluidity of the neutrons in the triplet state is about 5 to 10, 10 to the 8th Kelvin. The proton, we also require, or I'm not showing here is the proton superconducting profile and critical temperature, and that's much higher. So that's on the order of 2 times 10 to the 9 Kelvin, and so that's why at early times, and less than 100 years or so, the protons, while the protons are superconducting because the temperature has dropped below their higher critical temperature, it hasn't dropped below the neutron critical temperature, which is much lower. And so it's in between. And so those protons are superconducting and the neutrons are not yet at this early time. So we are constraining both so there is a difference there, and that the proton superconductivity gap energy is much higher. In terms of direct Erka, again, you do need, like you said, you do need that the protons are superconducting, and so it retains a high temperature at early times, so that once you turn on, allow for direct Erka to become in a small portion of the core, that you can get a rapid change. Oh, sorry, it's not that it's allowing, but that you have this combination of because the direct Erka is going to cool you very quickly.
Yes, right.
You wanted to keep it hot. So
right. A very special combination.
Just seeing it now.
Yeah.
So you do have to kind of tweak.
Fine tune that. Yeah.
I don't remember what the critical temperature for proton superconductivity in that scenario is. I would imagine it's Yeah, I'm not. I think it would have to be. I think the temperature could be comparable to what we need also, but you're adjusting where it is, where the gap in the in the neutron star is, because
you mean the profile itself?
yes, because you know the direct Earth is primarily going to occur deep in the core, so you want the gap to kind of overlap, maybe overlap or not, to kind of get the right.
I see. Right. I think you are right. I think this based on what Yakovlev and Kusakov they proposed early in 2004, initially to explain creaking neutron star cooling, but it seems also can explain alternatively for Cassiopeia. Thank you. I will look into their more recent works.
Okay, and I see Sanjay's hand.
Yeah, one more kind of crazy question. Is fallback, very, very late time fallback, a possible source of heating for the neutron star crust?
In Cassiopeia, I mean, I guess you could, if there was an earlier episode, like between when it was Cassiopeia was born, the neutron star was born, and 340 years or 320 years ago, I mean 320 years later, if there was some fallback and heating occurring in that period, maybe, because then you could keep the temperature high instead of proton, or in addition to proton superconductivity. You could do that. But it would, at least currently, it doesn't seem like it yeah, there's not much heating going on, because it's obviously cooling over time and stuff within the uncertainties. I would also say that if you want the fallback, it would have to occur, and the extra heating, it would have to occur either continuously, or it has to occur kind of roughly now, or roughly like 1900, when the matter became superfluid, and when it started this rapid drop out here, right? Because the neutron star cools very quickly, even if it's just accretion onto the surface. That doesn't heat it very much, and so it cools the neutron star would cool very rapidly. That extra heat, and so if you want to keep it kind of hot, it would have to be a lot, and it would have to be recent, so that it has a kind of measurable effect. I'm not sure if I came across clearly, but
yeah, I think that makes a lot of sense. So has anybody estimated how much, if it's a very recent accretion event, whether we should be seeing the accretion X-rays? Can we rule that scenario out?
Well, again, and I don't think you can put too tight of a, I mean, if we just look at so here are, if the accretion is occurring now, right, at the current time, then it'd have to be low enough that you're kind of hiding it within these measurements. I mean, there's some, a little bit of jumping around and stuff, but it's basically, as we say, it's declining at 2 to 3% per 10 years. So you could try to hide it in here. And so you can estimate that. Yeah. I mean, there's, yeah. I'll stop.
Okay. All right, thank you.
Okay, are there any more questions here as we approach the top of the hour? I see Prakash has put something in the chat. Prakash, would you like to ask a question, or should I just go ahead and read it?
You go ahead.
Okay. Is there a plan to observe Cas A's cooling since the last time?
Well, yes. Oh, I mean, we put in, I think, and so the last observation was 2019. From our sets, there's another, like I said, there's another one from 2020. I mean, we put in a proposal the last, I think, 2 times cycles for Chandra observation. We put in proposals, they've been turned down. So, I mean, we're gonna put one in again this year. So in March, hopefully gets approved. I mean, yeah. So I hope. But, I mean, if we got this year's approved, then it would the observation wouldn't happen until next year, so 2023. So that would, you know, that would give the would be a longer interval, but you know, it would increase the baseline by 4 years, right? So that would be nice.
Okay. Any last questions here before before the top of the hour? Okay, if not, then let's thank Wynn once again for a very nice talk. I'm going to stop the recording. I'm going to stop the recording. If people want to stick around for a little bit and have an even more informal discussion, then of course, please feel free to do so. Let me just stop the recording.